A model can be accurate overall and still treat people unfairly. This loan model is 85% accurate. That sounds fine, until we look at who it says yes to, and who it says no to. The model serves two groups of applicants. We'll call them Group A and Group B. And here's the key fact: on average, the two groups are equally qualified. The same share can genuinely repay. First, the headline number. Overall accuracy is 85%. On that single number, nothing looks wrong at all, but an average can quietly hide a lot. So let's stop averaging and split every result out by group. This is the habit that surfaces fairness problems. Always look at each group's numbers on their own. Start with the simplest question: what share of each group gets approved? Group A, 50%. Group B, only 28%. That's a 22-point gap between two groups that are equally qualified. Where did that come from? The model learned from historical data that already carried bias. At the very same true qualification, Group B had been scored lower in the past, and the model faithfully reproduced that pattern. To really see it, let's open up Group B's outcomes in a small table. Top row, the applicants who were truly qualified. Bottom row, those who weren't. Left column, approved. Right, denied. We fill it with the real counts. Now focus on the qualified row, the people who deserved a yes. Of those, how many actually got approved? That fraction is the true positive rate. 81 out of 81 plus 55, which is 60%. This is the number equal opportunity cares about. Do the same for Group A, and compare. Among qualified applicants, Group A is approved 92% of the time. Group B, just 60. A 33-point gap. Qualified people in Group B are being turned away far more often. Equal opportunity says those two bars should match. What about the other direction, the false alarm rate, approving people who weren't qualified? Group A, 13%. Group B, only 2%. So the harm is one-sided. Group B is held to a stricter bar coming and going. There's more than one way to define fairness, and they are not the same thing. Demographic parity wants equal approval rates across groups. Equal opportunity wants equal rates among the qualified. They sound similar, but watch. Suppose Group P is 60% qualified and Group Q only 40%, different base rates. Give both groups the exact same true positive rate, 90%. Equal opportunity is perfectly satisfied. Yet the approval rates still come out 58 versus 42%. Demographic parity is broken. When base rates differ, you cannot have both. You must choose. For our loan model, we'll choose equal opportunity. The fix is to give qualified Group B applicants the same shot as Group A, by lowering Group B's decision threshold. Here are Group B's qualified applicants, laid out by the score the model gave them. The old threshold sits here. Everyone to its left was denied, including many people who were genuinely qualified. Now we slide the threshold left, to match Group A's standard. Watch these applicants flip from denied to approved. 44 qualified people, wrongly rejected before, now get the yes they earned. Now the worry: did being fair cost us accuracy? It went from 85% up to 88%. It went UP, because the bias had been causing real mistakes, denying people who should have been approved. Be honest, though, here, fairness came for free, because it corrected genuine errors. But as we just saw, the definitions can conflict, and very often the fix does cost some accuracy. There is rarely a single correct answer. That's why fairness is a decision, not a formula. Measure every metric broken out by group. Choose the right definition together with the people affected. And keep monitoring. Gaps can reappear as the data shifts. So, overall accuracy can hide real harm to a group. Derive the true positive and false positive rates for each group from the actual counts. Know that the fairness definitions can genuinely conflict. Choose one deliberately, and then monitor it over time. Next, we turn to protecting the private data these models are built on.